Batmanathan, Reddy. He is going to present numerical approximation of variational inequalities arising in elastoplasticity. Before he is going to give a talk, I'd like to introduce him a little bit. He has the South American Research Chair in Computational Mechanics at the University of Cape, and he got his PhD in University of Cambridge, and he has been a faculty member at the University of Cape since 1979 and served as a DM for 6 years, and he's an elected fellow of various national and international academics, and he's currently the president of Academy of Science of South Africa. And yeah, he is an elected fellow of International Association of Computational Mechanics, and also he got George Forster Prize from Germany, and his research interest area are various intersections of continuum mechanics, applied functional analysis, and numerical analysis and computing, especially finite element area. Okay, so let's him give a big hand. Okay.
Thank you very much, Chair. And I must say it's an honor to be here, to be able to speak here in this session. And I'm grateful to the organizers of this particular session for inviting me. So there are various topics that, in a sense, I want to bring together in this talk. One has to do with a particular class of problem that arises in solid mechanics, and which happens to be formulated as a variation inequality. So I'd like to spend some time talking about those, and then I want to say something about how one goes about solving them approximately. So what I thought I would do is really just kind of set out how I would think about approaching problems of this kind in the context of mechanics of continuous media, mechanics of solids and fluids. So to begin with, one develops a mathematical model. In my case, the model is there. And in most cases, these would take the form of partial differential equations. Here, we will see that there are inequalities as well. I think it's important also to study the well-posedness of the model, to have a sense of the behavior, the nature of solutions, the circumstances under which one can expect solutions to exist, before going on then to considering methods for finding approximate solutions. Again, with the approximations, I think it's important also to analyze the conditions under which those approximations will in fact converge and converge to the exact solution. And then, of course, last but not least at all, is the business of actually implementing these, typically on the computer, developing the algorithms for doing so, and doing the coding and all that. All right, so really just to, in a sense, take one step back to set the scene, let me run very quickly through a simple problem, which I'm sure we're all familiar with, namely the heat equation. So I have a single scalar valued variable, temperature. We have a balance equation or a conservation equation, in this case balance of energy, in which we see the heat flux Q, the heat flux vector, and on the right-hand side, a heat source term. Then we need something that tells us how a particular material is going to conduct heat, a constitutive equation or relation, in this case Fourier's law, which relates the heat flux to the temperature gradient, and we have a constant there, the thermal conductivity. Well, we put these together, substitute Q in here, and we obtain the well-known heat equation. If the material is homogeneous, in other words, if the properties do not vary with position, then I may take the K out of here, and the equation takes this form, or more simply, the second term on the left-hand side is still across. All right, so that's how we would go about, in a sense, obtaining the heat equation. So, let me go now to a problem in elasticity, linearized elasticity to be precise, where I'll go through a similar series of steps. The first difference is that now I have a vector value variable, which is the displacement. So the displacement measures the motion or the movement of a point to a deformed position under some action of loads and the like. And now the analog of the balance of energy is balance of momentum, in fact, which is the equation of motion. It's second order in time, and I have a term here, instead of the heat flux, I've got the stress, which is a tensor or matrix valued function. The analog of Fourier's law would be the elastic relation, which tells me that the stress is related to the strain, which is the symmetric gradient. So instead of just grad of temperature, I've got the symmetric gradient in this instance here. And it's a very simple linear relationship where lambda and mu are two material parameters. So again, I can now put everything together, substitute for the stress in here, substitute for the strain in terms of the displacement, and that will give me finally what is called the Lame equation, where I have a partial differential operator, which I've called delta bar, with a nod to the Laplacian, which of course looks a little different in the sense that it's got a grad div and a div grad term with some material constants in front of it. Okay? So that then, in a nutshell, is what the problem for elasticity looks like. If the data is independent of time, I just had some loading acting on the body, which does not vary with time, then I can throw away the time derivatives, and I have what we call the equilibrium equation. And I've put down here a very simple boundary condition just for convenience. Okay, later on I'm going to be talking about variational inequalities, and so we need to just know a little bit about how one would go from the problem on the previous slide to its variational formulation. Essentially, one does so by, if I go back one slide, one does so by taking this differential equation here and in a formal way taking the inner product with an arbitrary function v, integrating by parts, invoking the boundary condition and so on. And we end up, let me start down here, we end up with a problem, an equation that looks like this. Find u in a certain function space that satisfies this equation here for all functions v in that same space. So this here is a bilinear form. It's linear in each of the slots, and you can see that it derives from the Lame operator. L is a linear function which takes care of the source term or the loading term. And V is my space of admissible displacements. These are functions which are square integrable. I need that because of these integrals here. Their first derivatives are also square integrable, and they satisfy the boundary condition V to 0. So there I have a complete statement of my problem, and using a fairly standard approach, one can show that this problem has a unique solution if the bilinear form A is continuous, meaning that there, where that is the norm of V, and it's also V elliptic, so it satisfies a certain growth condition. Both of these are satisfied in the case of this particular problem because of the properties of these material parameters lambda and mu. So as far as the elasticity problem is concerned, there in a sense we have the full whole story. Well, those are two examples of problems that take the form of partial differential equations or systems. Let's look at something a little different now. So this is a classical problem, the obstacle problem. And the problem is as follows. I have think of this as a membrane that straddles a rigid or a solid boundary or obstacle. It is subjected to some sort of loading along here. Because of the obstacle, whichever way it deforms, it has to be such that this inequality is satisfied. In other words, u, the displacement, has to be greater than or equal to the function g of x that describes the obstacle. And furthermore, this term on the left-hand side represents the net force. So the Laplacian of u, the internal force, and F will be the external force. And what that is saying is that the net force must be non-negative. In other words, either it will be equal to 0 here, or in other words, where I have contact, or otherwise it must be positive. But I have to have the condition that one or the other of these two is 0. So either I am at the obstacle, in which case u is equal to g, so that is 0, or otherwise I'm somewhere else, not at the obstacle, in which case the net force acting on the membrane is equal to 0. So this is called a set of complementarity conditions, and one can go through the business of setting up the problem again. This time I'll use the same space as that which I defined for the elasticity problem, but this time for a scalar, and this time I have this constraint here, that my admissible displacements must satisfy that, if you like, that geometric condition. So this is not a subspace, it's now a convex subset. And because of that, because of these inequalities, I no longer have an equation here which would otherwise have been A of u to be equals L of v. I now have an inequality, and that's called a variational inequality, which I have to pose on that convex set there, and I require that this be this hold for all v in that set. Here, very quickly, is an example of a different kind of variation inequality, one which will be closer to what I'm interested in. This is what is called a Bingham fluid. So it's quite easy to understand how it works. Well, we know about the stress from an earlier slide. Epsilon of v is the velocity, epsilon is the symmetric gradient. So this measures the rate of deformation, the rate at which deformation of the fluid takes place. What it says is that if the stress, or the stress deviator, which is a little technicality, is less than or equal to a certain threshold, nothing happens. All right? So in those regions of the fluid where the stress is not high enough, nothing happens. It's essentially rigid. However, when that threshold is exceeded, then one has flow in this way here, in which the rate of deformation is parallel to the stress deviator, and we have something in front of it. Now, it takes some work to go from all of this together with the equation of motion to the variational problem. But the important thing about it is that I've got a simple looking bilinear form here, more or less as before. But now I have a function here, g. The integrand is g times the magnitude of that strain, the magnitude of the symmetric gradient, which is not differentiable at the origin. It's essentially, it looks like a curve. Okay? And because of that lack of differentiability at the origin, I end up once again with an inequality, a variational inequality, posed on the whole space, but now an inequality because this function of j, or its integrand, is not differentiable. All right, one can go on from there. So if I just go back quickly to this variation inequality here, one can consider variational inequalities in which there is a time term as well, the sort of first derivative that you get with the heat equation, but with constraints that lead to your problem taking the form of a variational inequality rather than an equation. I'm not going to spend too much time on the definition of these function spaces. I'll say more about them as and when I need them. Now, I want you to just bear in mind that what I've done here in introducing this parabolic variation inequality is essentially to have added this term in front, which, as I said, would be something like the first derivative term you have in the heat equation. For my main problem, which is that of elastoplasticity, the variation inequality takes a different form. It takes this form over here. I don't have that term in front that you saw a moment ago, but now what I have is instead of A of W, Z minus W, and so on, I've got a W dot there, okay? So, once again, I have a variation inequality in time, although I don't have the first derivative term that you would have in the heat equation, or the second derivative term that you have in elasticity. So, this here is a bilinear form, and you can think of the kind of bilinear form I showed a moment ago. This here would typically be, well, it is in fact convex and positively one-homogeneous, so think of a mod function, so not differentiable at the origin, and L is linear. So, the point then is that this variation inequality arises, well, in more than one context, but most particularly in the context of elastoplasticity. So I'd like you to spend a couple of slides showing you where it comes from, and then I'll come back to it and we'll talk some more about its approximation and so on. So, well, you remember elasticity. Now, in the case of elasticity, we have, well, from a physical, from a mechanical point of view, if I remove the loading, the body returns to its original shape, right? It's completely reversible, the behavior. Plasticity aims to take account of irreversible behavior. So I now have an additional variable, P, the plastic strain, which measures irreversible behavior. Think of if you bend a metal rod sufficiently, of course, it doesn't return to its original shape. And the accumulated plastic strain defined in this way, oops, there's a mistake there, which I treat as an independent variable. Now, instead of that relationship there that we had for elasticity, I now have a relationship here, so that's the total strain minus the plastic strain. I've got an additional variable, which is this plastic strain. I need an additional something, and that something turns out to be a variational inequality. So there's quite a lot here, but let's just go through it. I have a function here which is not differentiable at the origin. It might look rather strange in that it depends on both these variables, the plastic strain and the accumulated quantity, and it's plus infinity if that mod Q is greater than sigma, otherwise mod of Q, which again is a cone. So that defines D. My functional J is the integral of D, and so I have an inequality involving D and then the stress and additional terms. There's a term with a constant K1 there and a term with constant K2. These are additional terms that characterize what is called hardening, the way in which plastic behavior takes place, right? So there's quite a lot there, but let's look at where this comes from. So let me take a very simple case, the scalar case. I'll switch off K1 and K2. And take D of P dot of that form, which is the standard form for it. So if P dot's not 0, I can differentiate it. And if I differentiate it, it's sigma 0 times the sine of P dot. If P dot is not 0, then all I can say is that sigma q is less than or equal to sigma 0 mod q, or another way of writing it is like this here. I can take all of this and package it in the form of this inequality. In other words, this inequality tells me that, and it tells me that as well, and that is the great advantage of it. The complication arises because D looks like this. It's not differentiable at the origin, and so here is where we have the complicated behavior. Okay, so the weak formulation, I need to define function spaces. So I have my displacements, I have the plastic strains, which are not differentiated anywhere. There are no derivatives of them, so it's good enough for them to be in L2, and the accumulated plastic strain, the same thing. Then I can define a product space, and there is my equilibrium equation from before, and here is what I showed you just a moment ago, the equation that governs plastic behavior. So still looking a little complicated, but I can put these two together in the form of a single variation inequality by defining a bilinear form like that. So the two terms of the K1 and K2 down here, and the J term, and if I put that all together, it looks like this, which is exactly the form of that abstract variation inequality I showed earlier, which is not standard, and therefore which is something which we've spent a lot of time studying, both theoretically and computationally. Fine. Well, just a quick word about the well-posedness, because as I said, it's important to understand the conditions under which one does have a unique solution. So, it's something I worked on a long time ago. We came back to it a little later, and more recently we've looked at further extensions of it. But in a nutshell, under the conditions that I've set, and with J in particular being positively homogeneous, we have a unique solution, which is in H1 in time. In other words, what this says is that W is L2 in time, square integral in time, and so is its first derivative. Well, the approach to the proof is nothing too special. Essentially, one introduces a time discretization that you know how to solve, and then look at the sequence and take the limit of the sequence. In fact, here is the time discrete problem, which I do want to say more about. So we partition the time interval in a uniform way, just for convenience. Uppercase delta is the difference between the solution of the two time steps, and lowercase delta is the divided difference. So here is my variation inequality. Looks, if I go back to the previous, essentially I've replaced the W dots by delta W over K, all right, or delta W over delta T, and use the homogeneity of J to get rid of the time interval K. So that, in other words, that looks exactly the same. And I can write W in as delta W plus W from the previous time step, so I can write a variation inequality entirely with delta W as my unknown, with, of course, the right-hand side varying slightly. So, right, where are we? Just to summarize quickly, I've introduced a variation inequality, which is a sort of parabolic. I've introduced a time discretization of it. I've shown you the connection to elastoplasticity, but now I'm going to spend some time just looking at that variation inequality. These are time discretizations. Let me say a word about spatially discrete approximation. So I like to use the finite element method. And for those who are not familiar with the method, essentially the idea is I've got the original problem posed in some Hilbert space. I want to pose it on a finite dimensional space which will allow me to solve it, say on a computer. And I want this space to be such that it has some sort of parameter in the finite element method. It would be the mesh size, which when that parameter goes to 0, I will approach the function in the original space. So I have a way of approximating functions as closely as I wish in the original space. So essentially one would take a domain here as a rather complicated looking domain, partition it into, in this case these would be tetrahedra, they would look like this. My basis would comprise functions that are continuous and are polynomials on each of these little elements. So here you see a better picture. So for something like the heat equation, say, this is exactly what I would do. And based on finite element interpolation theory, I know that if I use the simplest, meaning the lowest order approximation, I will have, this is known as Seoul's lemma. It tells me that my solution, rather my error in the solution, is bounded by something involving the shortest distance between my exact solution and any function in the discrete space. And I can then use interpolation theory to get a rate of convergence from that. So that's how the finite element method works. In the case of fully discrete approximations now by variation inequalities, let me go back to that. So there it is as before. I've got the small delta here, meaning the divided difference. What we have shown is that the total error, well, the error between my exact solution calculated at time tn and my fully discrete solution, that is discrete in space and time, is bounded by a constant times k, which is the time step, and then something here which looks a lot more complicated and which takes care of the spatial side of the error. Let me just say that the order k could be improved if I use, for example, a Crank-Nicolson approximation. I just haven't shown that. As far as this over here goes, if I choose linears for my linear approximations for my displacement, like I showed a moment ago, and constants for the plastic strain, because I don't differentiate these anywhere, then I have an error, a spatial error of order h². One can obtain an error of order h, which in a way is what you would want, which is what one would regard as optimal. Carsten some time ago showed that by approximating the data in a certain way by element-wise averages and so on, and some further hard work, one could in fact, under certain conditions, obtain an optimal error. Okay, now a word about convergence under minimal regularity. So in that error analysis that the result of which I showed you, there's the assumption that my solution is, my displacement is h2. That's an error, that should be h1. That is actually smoother than is generally the case. So in recent work by Dorothee Knees, for example, she showed that the displacement components are in h to the 3/2 minus a small number, and the plastic strains are less regular than that, as one would expect. Which leads one to the question of can one show convergence without making this rather restrictive assumption? The answer is yes. This is some work we did some time ago. Assuming no more regularity than what you have in your variation formulation. However, you don't get a rate of convergence out of that. We simply get this here because essentially we set up approximations that are dense and so on. So we don't have a rate of convergence, but we are able to show convergence without making extravagant assumptions about regularity. Okay, let's skip that. Right, to come to what's it, the third part now of the talk, just to give you a roadmap as to what I want to do next. I want to look in more detail at the time discrete problem, because this really brings us to the heart of the matter. You've got a complicated inequality. How do you solve that? How does one solve that on the computer, and how do you solve it in an efficient way and a way which is convergent and stable? So I'm not going to worry about the finite elements. It suffices for us to look at the time discrete problem. And I'm not going to carry the deltas all over. I don't need that, so let's just drop the delta. So here I've got a simple looking variation inequality. But I really want to make a connection with the way people solve this problem in mechanical contexts like plasticity. Friction is another application that arises. And the point is that I showed you that the inequality that I had obtained by combining an equation, equilibrium equation, and an equation for the plastic flow. So let me go back to that structure. In other words, my A here, W really comprises two variables. It's a pair, and Z is an arbitrary pair. And this A here can be broken up into 4 terms, essentially involving all the combinations of the two pairs. Right? Once I do that, I can then split this problem up here into an equation and an inequality. Exactly like what we have for the plasticity problem. And this will be the basis of a predictor-corrector algorithm, where I would start with the one to get a predictor and then go to the second one to get a corrector. So for the plasticity problem, here is the bilinear form, and in fact the 4 expressions look like that, one involving only U and V. That involves the cross terms, and this involves only the plastic quantity. So that's how it breaks up in the case of plasticity. So the predictor-corrector algorithm, how does it work? Well, I've just repeated this equation and inequality. So we go about as follows. We start with some initial guess, and then for the predictor step, I compute my ith iterate of u, let's call it displacement, and for lambda, which would be plastic strain in that context, I compute an intermediate value, which is why I've got a star on it. I'm going to throw it away eventually. And I'm going to compute these, which solve this problem. So there's my equation, and I'm replacing my non-differentiable j by an approximation which is differentiable. So this here I could, in fact, have written as the derivative, the gather derivative of j. So I've got a pair of equations, easy to solve. Now once I've done that, take my ui and go forward now to the second, to the inequality, which is slow inequality, and now solve for lambda I. Okay? So that's the predictor-corrector procedure. How do I approximate j? Well, this is one way that works, that can be shown to lead to a convergent solution. So the solid line there is d, or think of the integrand d, which is a cone, and the approximation has the same value. Di has the same value as d at the previous iterate. The gradients have the same value as well, and the cone is always below its smooth approximation. It doesn't have to look like that, by the way. I just need this somewhere there locally, so that's not a good diagram. And then for the predictor step, one can then define a di that looks something like this here, and this would in fact satisfy these conditions. This is a very popular choice used in practice, in large-scale computations, which leads to quadratically convergent and stable solutions. Right. Does all of that converge? The answer is yes. And again, under certain conditions, on the B, C, and D, the three bilinear forms that make up the big one finds in the proof a combination of terms of this formula that tell you something about how B, C, and D are bounded either below or above. If that is less than a third, then the algorithm converges. I haven't shown why, but it converges in the sense that the difference between two iterates is bounded by this R1 over here raised to a power I. And R is, well, not that, but this here raised to a power I. That's less than 1, so it goes to 0. And then one has this kind of error estimate as well in terms of the difference between the iteratives of the previous two steps. What does this mean in the case of plasticity? Well, in the case of plasticity, what that constant looks like is something like this here. You see the K1 and K2 coming in here. Without those, I can't guarantee convergence. In fact, this result is a little too strong because you do have convergence in selected situations when K1 and K2 are 0. But I do need a sufficiently high degree of hardening, in other words, K1 or K2 large enough to ensure that R1 is less than a third, and therefore I can guarantee convergence. About 10 minutes? Okay. All right. So I'm going to. Okay. Let me just say a word about this, because if I go back to my predictor corrector algorithm, so the corrector step says solve this. So there still remains the question: how am I going to solve that? Okay. Well, the way in which we do it in the plasticity community, in fact, is not to work with that, but to work with its dual form, which in a way is the more basic form. So, the dual form comes about as follows. That is what we're familiar with. So, sigma is in the subdifferential of D. That's my variation inequality, more or less. Its dual form, I swap these around, so the dual form is that P dot is in the subdifferential of the indicator function of I, which is just a long-winded way of saying that P dot is in the normal cone to some elastic region at sigma. So it's much easier if one looks at a picture of this. So think of this as a level set of D. So I've deliberately chosen a D that is not smooth. So think of this as a cone, and this is just a level set. And there is a sigma, and there is a P dot. So those two go together, and sigma is normal there, it's unique. For a P dot here, the normal is not unique, which is why it's an inclusion and not an equation. The dual part looks like this. So there's my P dot, there it is again. There is that sigma, there it is there. So that sigma goes with that P dot, which is one possible normal there. And if I take the other P dot, which is this one here, there it is there as the unique normal along this edge, corresponding to which I've got a whole family of sigmas, which is this family over there. Okay? Anyway, the point is that I can rewrite it as this, what is called a normality condition. And that is what we use in practice, because what we do is we say, all right, let's take the stress at time step n, and let me write it as the strain at time step n minus the plastic strain from the previous time step, and there's the increment. So I can think of this as a trial, what I would get if I didn't have a delta P for my next step. And let's suppose that is somewhere up there, and here is my elastic region. then what one can show is that my actual stress I can obtain simply by a closest point projection onto that region. And that is a very efficient and simple way of solving the problem computationally. All right, finally, what is all of this good for? I thought I'd show you an example for this is for a model of plasticity which is a little more sophisticated than what I've shown you. It's a model that includes gradients, and the reason why that extension has been made is because at the scale of tens to hundreds of microns, so the thickness of a hair is less than 100 microns. At those scales, at the meso scale, there are certain what are called size effects that are apparent, which the theory that I've just been talking about is not able to capture. So here's an example of an experiment. This is a column of pure nickel, so it's been machined out of a block of nickel. The scale is, that scale there, in case you can't read it, is 10 microns. So this column is, it's less than 100 microns high, and it's subjected to compression. That's what it looks like there. And depending on the size of this column, so the biggest one would be corresponding to the black curve here that does this. As it gets smaller, we go to this mauve, light blue, the green. Smaller, it apparently becomes progressively stronger, which is the size effect. So this is something that we were trying to study and trying, in fact, to simulate these kinds of results here and to identify the length scales that occur in these sorts of problems. Anyway, that's just one particular example. So let me finish up here. What I've tried to do then is to show you how a certain variation inequality that is relevant to problems in plasticity can be analyzed, what its structure is, what makes it different to more classical variation inequalities. I've looked at fully discrete approximations, in other words, what happens when we approximate both in time and in space, the latter using the finite element method. With regard to time discretization, I've talked about a predictor-corrector algorithm, which is one that is very, very widely used in the engineering community, and shown, or at least established conditions under which that algorithm converges. And then I've also shown how we, in fact, calculate or compute the corrector step using a closest point projection. I've talked a little bit about convergence under conditions of minimal regularity, which is an important theoretical point. And lastly, just to say that this is well, it's a nonlinear problem because it's a variation inequality, but the inequality aside, the problem is linear. The full problem involving large deformations is highly nonlinear, is much more complex, and that is something that we've been working on steadily for the last little while. So with that, I'll stop, and thank you very much.
Thank you. Can you hear? Okay. Do you have any questions? Please.
Yeah. I'm thankful for your nice presentation. I have read your several papers and book also. In the classical variation inequalities, people are studying inverse problem. The direct problem usually there, but the inverse problem some people are studying. Then sensitivity analysis also myself and some Martin Bocante we have studied in some cases. Whether this kind of problems have been studied for the variation inequality which you have considered today and which you considered earlier.
You mean for
inverse problem
inverse problems
and sensitivity analysis?
Yes. You know, the short answer is I don't know, but I don't think there's been much work on it. I think I would have been aware of it. So it's a good question actually, and you know, as you're indicating, whether you're looking at inverse problems or sensitivity, one can easily describe situations that lead to variation inequalities. But I really don't think they've been studied, certainly not in detail.
And I wonder, the finite element you are using, usually now the virtual element method,
Yes.
are the wavelet methods also some people are using for finding the solution of variational inequalities. Some Italian mathematicians.
Oh, you mean the talk that Professor Brezzi gave?
Him and some other people.
Yeah. Well, actually, that's exactly what we are looking at with regard to the nonlinear problem, because my interest in the virtual element method in this context, actually is this one? In this context is that when you have nonlinear problems, your domain deforms very severely. So if you think about elements, and think particularly about elements that are, say, quadrilaterals, they deform very severely. The angles approach 180 degrees. In the classical finite element, you have big problems that way. With the virtual element method, it's not an issue. So in fact, that is precisely what we are trying to do at the moment, to apply the method that Franco Brezzi spoke about to nonlinear problems where you have severe deformations.
Thank you. Any more questions or comments, please?
Once you regularize, you have the variational inequality, you regularize the J.
Yes.
I guess you can prove the convergence of the solutions of the regularized solution towards the original one. Do you have some result about the free boundaries? If the regularized free boundaries converge to the original one or something like that?
No, that's a good question also. If I understand you correctly, you go to the predictor corrector algorithm, but by the regularized problem, you mean the one with the Ji. Okay, so that's a smooth problem. And of course, that does not give us the exact solution. It gives us an estimate, at least, of Ui. It would certainly correspond to an approximation to the exact solution, meaning with the partition of the domain into the elastic and plastic boundary and an approximation of the interface. But I haven't looked at that. That's an interesting question, because it would certainly be one way of approaching the free boundary if one is interested in finding the free boundary, the interface.
Okay, any more questions? Okay, thank you so much for a detailed and great talk, and please give him a big hand. Thank you.